Hi, this is a video on the law of large numbers and expected value. If you need this worksheet, you can get it on my website at caraleemath.com. So let's start with the law of large numbers. It is actually very intuitive, whether the name sounds like it or not. What that's saying is if you're doing an experiment, say coin flips, repeated with lots and lots of trials, then the number of heads that you get should equal, in the long run, it should come out to 50-50. In other words, the experimental probability or empirical probability in the long run should get closer and closer to the theoretical probability. So think about a coin for a second. If we flip a coin, we might start out with getting a lot more tails or a lot more heads. But the more and more trials we do, we should get closer and closer to that 50-50 mark. So that's really important to know, and I think you know it already. It's very, it makes a lot of sense. The more you flip, the closer you're going to get. So let's look at a problem where we can examine this. Example 1, Theo rolled a standard 6-sided die 1,000 times, and he recorded that the number 2 came up 100 times. He suspects the die is not fair. Is he correct? So here's a standard die. We've got 6 sides. So they should all be equally likely. If the die is fair, that means each side is equally likely to come up. Okay, so what would we expect to happen? And this is 1,000, it's quite a large number. It's a lot of times to roll a die. So we would expect, since there's 6 sides, we would expect to get a 2 1/6 of the time. So let's write that down. Okay, we'd expect it to 1/6 of the time. So if we do 1/6 times 1,000, what do we get? Does it seem like 100 is lower than that? Yeah, that's actually 1/10, right? So that seems pretty low. Okay, let's check it out on the calculator. So I'm going to use my fraction key first, fraction function first, times 1,000. And if you come up with a reduced fraction, you need to hit the decimal button. 166 or 167 times, I'm going to round this. So we would actually expect it to 167 times. Now if you want to use a decimal instead, you can do 1 divided by 6 first to get your 1/6, and then multiply by 1,000. That's another way to get it. 167 times. So what do you think? You think it's a fair die? 100 is pretty low. Now, is this just, oh, we haven't rolled enough? And if we roll more, it'll get closer and closer to the 167. Seems like this is a little on the low side. So it's only 1/10. So it looks like it's probably not a fair die. Let's put, it seems like it's not a fair die. Okay, so gambler's fallacy is related to this. This is another fallacy that, let's go back to the coins. Let's say you've got a long streak of tails going. Does that mean that heads is more likely to come up the next time? And sometimes a lot of people think this, oh, I've got a lot of tails, so I'm more likely to get a heads next time. But that's not actually true. We know that in the long run we're going to get towards 50-50, but still every coin flip is independent of the flip of any previous flips. Every flip is independent of every flip. So just having a long streak doesn't make you, less likely to get that same value or more likely to get the opposite value. So watch out for that. That's a gambler's fallacy. The mistaken belief that a streak or run of bad luck will make the opposite outcome more likely. Okay, so now let's talk about expected value. This is the long run average or mean for many repeated samples. Now we've already actually looked at expected value because we actually calculated that right here. So to use the die as an example, we expect to get 1/6 of the time to for the die to land on a 2. So the expected value for the number 2 is actually 167. Okay, let's look at a different type of example. Down here in example 2, I have a lottery ticket. And there's 4 different things you can win, or also you can win nothing. Should have put my $sign on there. Okay, these are the amounts you can win. So what if we just took an average of those? And we did 1 plus 10 plus 50 plus 1,000. Add that up and divide by 4. So that's the average of all the amounts you can win, right? However, it's a lot more likely to get $1 than it is to get $1,000. So this is not the kind of average that we're going to use. So the expected value, it is an average, but it's weighted by the probability. So things that are more likely should factor more into the average, and things that are less likely should factor less into the average. In fact, 0 is the most common, and so that should factor more into the average than any of the other dollar amounts. So the expected value is an average that's weighted by the probability. Or I'll say probabilities, because we have to have more than one possibility and then a probability for each one. Okay, so let's take this lottery ticket, move this up. Let's take this lottery ticket and actually find the expected value. How much would you expect to win? What we're going to do is multiply each prize by its probability. So we're going to take $1 times 1/5 plus $10 times 1/50 plus $50 times 1/100. So you can see these are getting less and less likely, so they're going to count a little bit less. And then plus 1,000 times 1 over 2,000 plus 0. Now when I multiply 0 by anything, it's going to stay 0, but I still want to write it in. I'm going to use the decimal version because it's a little bit easier to deal with. Okay, now let's go ahead and switch these over to decimals. You could also use a fraction button on your calculator. So let's do, this would be 1 times 1 divided by 5, or just 1/5, should be 0.2. This one will be 10 divided by 50, or 10 times 1 divided by 50. Multiply numerators and denominators. Interesting, also 0.2, or 20 cents. Yeah, I'll put my zeros on there. Okay, then we have 50 divided by 100, which is going to contribute 50 cents, plus 1,000 divided by 2,000, another 50 cents. And then this is 0. Okay, so let's add these up. We have $1.40. $1.40. So that's interesting. This is our expected value, and we always want to put units on the expected value. This is saying overall, in the long run average, we would expect to win $1.40 per ticket. Now, can we actually win $1.40? No. You can only win $1 or 10 or 50 or 1,000 or 0. But on the average, let's say you bought all the lottery tickets, you should on average expect to win $1.40 per ticket. Okay? Sounds okay? Yes? No? Sounds good? Well, it depends how much you're paying for the ticket, right? If it's a $1 ticket, that's great because you have a chance to make 40 cents more, but then the lottery commission would be losing money overall. That would be a problem for them. So part B says, if the cost of the ticket is $2, what are your expected winnings? Okay, so if we win $1.40, but we spent $2, so I'm going to subtract that, we're actually 60 cents in the hole on average. Okay, you might be wondering, why would I want to buy the lottery ticket? Well, because there's a chance you might get $1,000 or 50 or 10. So you're always playing that short-term odds, but in the long run, you know that it's not a winning proposition overall in the long run. So this is why they say lottery is to be played for entertainment only and not investment purposes, because in order for the lottery to function, they have costs and they have to pay out money, so they have expenses, and so every lottery is going to have a negative expected value for the players. It'll have a positive expected value for the lottery. Same thing with gambling. Gambling, casinos, every game is going to have a negative expected value for us, the players. Okay, makes sense so far? So the expected value is, think of it as a long run average. If you bought all the lottery tickets, or mean value, excuse me, for many repeated samples. Okay, so it is an average over time. Okay, let's do one more example of expected value. And this always has to do with probability, so games of chance or things that have an element of chance in them. So another great example of this is insurance. We buy insurance in case something happens, right? But what are the chances of something happening? And how much should insurance companies charge so that their expenses are covered? And there's just a lot of questions with insurance policies. So here's example 3. Primo Insurance sells an annual car insurance policy for $1,350. Doesn't sound like a great deal to me, but that's what they're charging. Based on past data collected, an average of 1 in 50 policyholders will file a $6,000 claim. An average of 1 in 100 policyholders will file a $15,000 claim. And an average of 1 in 30 policyholders will file a $33,000 claim. So this is good. They need to base their prices on past data, what they have experienced, even though that doesn't indicate what's going to happen in the future. Okay, so this time we need to make our probability model. In example 2, our probability model was already given to us, and then we calculated the expected value. But here we need to make it ourselves. So what we do is we list all the possible outcomes in the top row. So I've written insurance payout because that describes the outcomes, just like prize described the outcomes up here. So the insurance is paying out, let's skip this, we'll come back to this in a minute. So they're paying out $6,000, that's one possibility, and the chance of that is about 1 in 50, or 1 out of 50. Another option is they might have to pay a $15,000 claim, which is 1 out of 100. Another option is a $33,000 claim. Now this is oversimplified, right? Because in reality a claim could be a continuous any number from whatever the deductible. So here we're just kind of simplifying it to a few choices to make it easier. And that is 1 out of 300. Okay, now it's also possible that someone will not make any claim, right? That's 0. So always look for a 0 option, and we don't have any other options. Okay, so the first thing with our probability model is we need to find this number. We need to figure out what's the chance of getting 0. What's the chance that a customer will not file a claim? Okay, well we know that these all have to add to 1. So what we can do is do 1 minus 1/50th minus 1/100th minus 1/300th. And that will give us this value here. So I'm going to punch that in. You can switch to decimals if you feel more comfortable. I'm not too worried about it. 1 minus, I'm going to use my fraction button. 1 minus 1/50th minus 1/100th minus 1/300th. Comes out to 29 out of 30. Also, if you like working with fractions, you could get a common denominator and do the subtraction. It's kind of fun. 29 out of 30, we could also get a decimal for that. Okay, so now that we've got our insurance model, our probability model, now we can find the expected value. And that's the expected value that the insurance company will pay out per policy. Okay, so expected value is going to be 6,000 times 1/50 plus 15,000 times 1/100 plus 33,000 times 1/300 plus 0, and we know this term is going to be 0, but I still don't want to neglect it, so I'll put it on there. Let's change these into decimals. So this will be 6,000 divided by 50. It's $120. 15,000. Now I could just take 2 zeros off of there, right? That's how it should come up. 150. And let me switch over here, this side. 33,000, that should be 11 with 1 0. $110 plus $0. That doesn't add anything to the amount that they're going to pay out. Let's add these up. So we have 110 plus 150 plus 120. $380. And I want to emphasize this is per policy. Okay, because this is saying per customer that buys a policy, they have this chance of paying 6,000, this chance of paying 15,000, and this chance of paying 33,000. So overall, per policy, they're expected to have to pay $380. Okay, so what do you think about how much they're charging for this insurance policy? A little high, isn't it? Now, they have some costs, okay, so they've got to meet their overhead. Let's look at question B. What's the expected profit or loss per policy? Okay, so if we look at which ones are positive, which ones are negative here. So they're bringing in this amount. This is income for the insurance company. So they are making $1,350, and then they have to pay out, so this one will be negative, minus $380, and the difference is the amount that they get to keep. Their profit, maybe not their profit, but what they have to pay, all of their overhead, and then also profit. So let's find the difference. $1,350 minus $380 is $970. So let's write that out in a sentence so it's really clear what this means. The insurance company now I'm still going to put an average because this is an overall long run average of $970 per policy. Or we could have said expected, because not for sure, right? Something could happen the next year and there are a lot fewer claims than normal, or a lot more claims than normal. So this is based on past data, so it's what they expect, but there's no guarantee that that is going to actually happen. Okay, so that does it for this section. We looked at the law of large numbers, which is what happens over time. We expect that any trials will come out close to that theoretical probability over time. Gambler's fallacy, very important. And then we calculated the expected value with two different examples, which is the average that's weighted by the probabilities. So thank you for watching, and I'll see you in the next one.